When working with inverse trigonometric functions, we're also going to be interested in finding inverses of cosine and tangent. We'll start with the arc cosine, the inverse of cosine. Same idea as the sine function. If we continue the cos function on, cos starts at its peak, then goes down, but it would come back up. However, if we restrict our domain to 0 to pi, then on that interval, the cosine function passes the horizontal line test. And so we define this capital C cos function, which just limits the domain to that safe interval where we do pass the horizontal line test. We can't go any further because then we'd start getting duplicate y values again. Can't go any further back for the same reason. Notice it's a bit awkward in the sense that this interval is not the same interval as we had for the sine function. That was negative pi over 2 to pi over 2. It's just the nature of these graphs. Where is a stretch closest to 0, because we like that, where the function is invertible. So cosine, the interval that we choose, is 0 to pi. Once we have defined that narrow interval for the cosine function, giving it that capital C cos, then we can do the same thing we did with the sine function, and that is reflect it. It's a little less obvious what the graph looks like here, but you can see that this point at 0, 1 gets reflected to the point 1, 0. The point pi over 2, 0 gets reflected up to 0 pi over 2, and similarly for the final point here at pi negative 1 goes to negative 1 pi. And from there you can fill in the graph of the inverse or the arc cosine graph. Again, remembering this inverse, this negative 1 here means inverse and not reciprocal. It's not 1 over cosine. As a quick practice exercise, we can use the calculator to find the Arccos of 0.7. Again, making sure we're in radians because it's a calculus class. And we get a value of 0.795. Again, remembering that this is a ratio of side lengths, and this would be an angle, and so it would be in radians. Now what we can do is draw a triangle that would capture that relationship in a more visual way. What we can say is we're looking for a ratio of 0.7, and an easy way to do that is we define our adjacent and hypotenuse side. So let's do that as our angle theta. We're saying the ratio of the adjacent side to the hypotenuse is 0.7 to 1. If you liked, you could write that as 7 to 10. The beautiful thing about triangles is that it doesn't matter as long as the ratio is consistent. All you're doing is scaling the whole size. And what we found here as the angle in this particular triangle would be 0.795 radians. So the Arccos takes us from ratios of adjacent over hypotenuse to the angle that would be defined in a triangle there. Now, quick question. If we do this with Arccos of 2, let's take a quick stab at that. You get a math error when that happens, but it seems like a pretty reasonable calculation. Take a moment to think about why that might be the case. Why might we get an error when we compute Arccos of 2 with the calculator? Well, one of the things we can rule out pretty quickly is that it's too big a number to handle. 2 is a fine number. There might be mathematical issues, but that's not the one. The inverse, calculus does not understand the business of taking the inverse. That doesn't sound right because we're able to do inverses. We just did one on the last page. The cosine does not really have an inverse. No, that's not true either. It does if we limit the domain. That was our capital C cosine objective. And the issue is really this. What we'd be saying here is we have a ratio of adjacent over hypotenuse that's equal to 2. And so imagine what that would look like as a triangle. We would have the adjacent is 2 and the hypotenuse is 1, and that's just not possible as a triangle. We cannot build a triangle like that, so we can't have an input of 2 to this particular function. The domain of possible ratios for Arccos is going to be negative 1 to 1. We have to have the adjacent side smaller than the hypotenuse in any reasonable triangle. In the same vein, we can find an inverse of the tangent function. So the tangent function has this classic asymptotic shape, and usually, if we had the entire tan function, it would repeat itself an infinite number of times as we move to the right. However, if we want a domain where we pass the horizontal line test, we can't include these other branches or the ones that come later, because then we would be crossing the same y value at different x points. If we limit ourselves just to this interval here, negative pi over 2 to pi over 2, we have one smooth continuous version of the tangent function which does pass the horizontal line test. So we define capital T tan of x as the same as tan, no difference, except we limit ourselves to this negative pi over 2 to pi over 2 interval. Now that we have a part of the tangent function, we can define an inverse sensibly, and we do that simply by, again, reflecting across the y equals x line, replacing the meaning of the x coordinates with the meaning of the y coordinates. And what that does is it takes this vertical asymptote and turns it into a horizontal asymptote. And likewise on the other side, this branch here, which approaches x equals negative pi over 2, when we flip it or reflect it, now approaches y values of negative pi over 2. As a quick calculation test, what's the value of arctan of 1? Well, if we go to 1 here, we get a value, and it looks like it's about halfway. We can also go to our calculator, and when we do that, we get 0.785. That's not too indicative. The best way to look at this is to again draw a triangle, and in this case here, this is a ratio, and it's the ratio of opposite over adjacent. And if that's the case, the ratio is 1 to 1, so we can draw a triangle that's 1 by 1, and then we connect the hypotenuse there. Well, we already know that that's going to be a symmetric triangle here, and that means the angles here have to be 45 degrees, or exactly halfway up here, pi over 4 radians. So pi over 4 radians, or 0.785 radians, same value, coming most definitively, or most exactly, from a sketch of the triangle. It's worth making a quick note about the arctan function in particular, and some of its unique properties. We don't actually have that many functions in our toolkit that when we approach x equals positive infinity, or x goes towards positive infinity, we have a horizontal asymptote at one value, but when we go in the other direction, we approach a different horizontal asymptote. And it's worth noting that we can make statements about this using our limit terminology. If we take the limit as x approaches infinity of this function, we're going to get closer and closer to pi over 2. And so in the limit, the asymptote value is pi over 2. Whereas when we approach it from negative infinity, or approach towards negative infinity going to the left, then this function here, this graph, is going to get closer and closer and closer to negative pi over 2. So this harks back to what we mean when we talk about limits at infinity, and how we can see those values graphically if we have internalized the shapes of the functions that we're working with.